Oh, I'm recording. It's official now. All right. Are we starting everybody?
Well, I can go ahead and introduce you. It's just a couple of minutes before, but we have a pretty good turnout already. Um, you did have some business cards. Did you want to?
Yes. Yeah, Emmett told me to at least give his students business cards, but I'd like to yeah, hand them out to anybody in any of the imaging science students. Because I do have a double agenda here.
If you don't get one, I'm sure she has more. In fact, there's like a whole box down here.
Yeah, yeah. Oh, yeah. I'm not trying to recruit you guys. I like this department.
Okay, well, I see it's 3 o'clock and we definitely have a quorum, so we'll go ahead and get started. In case you don't know me, I'm John Caracas, one of the research faculty here in the center. And it's my pleasure today to be the host for Dr. Sanghui Han, who's here from CFD Research. And Sanghui is an alum of our program, but I'll just read a little bit of her bio here. She received her master's in imaging science 2015, and then her PhD in 2019 in imaging science. Since then, she's worked at the National Air and Space Intelligence Center. She's worked for DARPA. She's worked for the Air Force Research Lab, supporting them and pushing technical boundaries for image exploitation by analyzing radar phenomenology and integrating automated processing. He was a radar systems engineer with Resonance Sciences and KBR prior to joining CFD. And there she developed next generation imaging systems with adaptive capabilities, integrated AI algorithms, and resilient sensors for contested environments. So quite the background there. Actually, while she was studying for her MS, she was an Army intelligence officer serving overseas with specialized training in signals intelligence and electronic warfare. And during that time, she served assignments in Korea, Germany, and Afghanistan. And I think you were taking some of our online classes.
Yes.
During that time.
Although your class, I was in the States.
She came back to our team for her PhD. I had the pleasure of being her advisor, and she did a very extensive, wonderful PhD thesis, which is archived here at the library. And we're very happy to have her back today to speak more about her recent work and tell you a little bit about colorizing SAR imagery. So with that, let's welcome Simon.
Hi, thank you. Actually, this is not my more recent work. It's what I can present here. And well, I was making a presentation in the imaging science department, so I thought I need pretty pictures. I need cool images. The way you get cool images with radar is with colorized sub-aperture images. So I'm going to talk a little bit about SAR and how radar is used to form images and how colorized sub-aperture images are formed. That didn't work. All right, and like I said, John said a lot of words, and I see a few of you guys had like a snicker because it's code for a lot of different things. But the physics and the science behind it is the same, and it is creating images, but it's more than just creating images. It's learning something about the environment that you want to look at, right? And so, yeah, I have this quote by Leonardo da Vinci because he was a scientist and an artist. And in some ways, I feel like as imaging scientists, we're both scientists and artists, right? And these are actually all the components you learn about in all your classes, right? Whether it's human visual systems or remote sensing, Or what are some of the classes you take here? And agenda, I'm going to go through a little bit of an introduction. So comparing passive imagery or EOIR to radar images, since I'm assuming a lot of you already have some background in passive imagery, passive sensing, since that's what your classes are composed of. And last I checked, I don't think the classes have changed that much, right? It hasn't been that long, right? And then kind of talk about some key points. So resolution, that's something I've debated many times with myself and with people that do passive imaging with radar imaging. And so that's a key component of image quality. And so I'm going to talk about the differences. Color. So how is color different in radar images versus passive images? And then some examples, cool pictures. That's what you're here for, right? To see some cool pictures. And then some interpretations. All right. So some of the differences or key components of images, it's illumination. You first need illumination of some sort to get an image, right? And then you have all these artifacts, the undesirables of an image, whether it's noise, whether it's blur, speckle, and so the different things that causes that in an image. And then radiometry, where's Emmett? His class. And the pixel, what forms a pixel? It's a little bit different with radar images than from regular EO images, and then different products that you can get. And I just list a couple here. I know there's way more than just panchromatic, RGB, false color composite, but that's just what I thought of. That's more single band, wide band. I didn't want to touch hyperspectral here because that opens up a whole different can of worms. But yeah. So illumination for EOIR images, you have the sun. The sun is your primary source of illumination. For radar images, your illumination is from the transmitted radar bandwidth. So it's this beam of energy that's shot out into the world to illuminate an area. And then the way you form images is for that energy to come back to the receiver. Right? For EOIR, you have shot noise, which is the Gaussian distribution of photons that bounce around. And then you have diffraction. The Grover's, if you're taking Grover's class, then you should know what that is. It's the point spread function. And that plays a big role in radar as well, but but then for radar, you have interference. So if you, I don't know if Grover's already talked about this yet, but with EOIR, you're talking about the light is incoherent light. And so with incoherent light, the Fourier transform of a triangular function is a sinc squared function, right? Which is why you get the airy disk. That's what it's called. The airy disk of the point spread function. With radar, it's coherent light, which means your aperture function is the rectangular function. If you take the Fourier transform of that, it's a regular sinc function, which means you have minuses as well as pluses, unlike the sinc squared function where it's all positive. And so when you add a whole bunch of signals together, which is essentially what a Fourier transform is, right? It's an integration. Yeah, he was just saying that earlier today. It's an integration. So you get constructive interference and destructive interference, which is where you get all that speckle. So that graininess of a SAR image that you see is actually from interference. And then beam width, it's the shape of the beam that is sent out into the world that you're trying to get a signal back from. And then for radiometry, Emmett's class, watts per meter square per steradian, which is what goes back into the sensor. For SAR imagery, it's the relative return power. So energy is sent out into the world, it's scattered by whatever that energy hits, and then you're receiving it back. And it's the relative power of what you receive when that energy isn't sent out to what comes back. So there's actually a relativity to this. So if you're looking at an area where you have huge differences in the power that comes back, then it makes forming your image harder. Whereas if you're sending power out into a mostly open, very quiet, unnoisy region, then the equations on how to form images for that changes. So yeah. And then pixel, what makes a pixel? It's your detector pixel pitch, your resolution is based on focal length, and the distance of the sensor. For radar images, it's the bandwidth and dwell. So what's the bandwidth of the energy you send out, and then how long can you stare at it? So a bit different. So what do you notice that's not part of a radar image that's a key factor in passive image, in the passive imagery? Distance. So radar images really don't depend on distance. So the pixels that are formed by radar images, distance doesn't matter. It does, but not really. So at least not informing the pixel. So yeah, whereas passive imagery, distance is a huge part of resolution, right? The closer you are to an object, the higher resolution you can get, especially if you're talking about satellites. The closer the satellite system is to what it's imaging, the better resolution you get, right? Higher GSD or lower GSD is better, right? Yeah, and then some of the products, panchromatic, RGB, false color composite, thermal, very hot topic these days. Yeah, high demand sensor these days. And then with SAR, you have your CPHD or coherent phase history, and then what we call SICIDs and WIBIDs. So SICIDs, it's the sensor independent coherent data, and then WIBIDs is one name. It's the NGA, I guess, normalized name for anything that's been processed to look like an image, look like a panchromatic image. So there's a lot of things that need to happen for radar images to resemble panchromatic images. And it's all the processing that's gone through to make it look as close to panchromatic images as possible. But then these days, there's a lot of commercial companies that do create radar images, and some of them call it GEO, SLC, GRD. So you have your pure form, just the pure IQ data that's processed in some way. That's your CPHD. So that's the pure radar signal that comes back from the signal you sent out. And then SICID is that process to some degree. but not that much. And then WIBIT is the highly processed. As a scientist, it's actually really not that useful because everything's been processed out. But for an image analyst, that's what they primarily use. Because it looks as close to a panchromatic image as possible. And then what we're here to talk about, CSI, Colorized Sub-aperture Image. All right, so resolution. Well, in 2D SAR images, you have 2 dimensions. But it's called something a little bit different. So in regular images and passive imaging, we call it height and width, right? Well, for SAR, because it's not quite that simple, it doesn't translate quite straightforward. We call it range and cross range. So range is the direction perpendicular to the platform of the sensor. Cross range is the part that is parallel to that. So X and Y kind of, but we call it range and cross range because it's not really parallel. It's not exactly X and Y. Or it's also called fast time and slow time, which is a little more intuitive. So fast time, it's called fast time because it refers to the packet of energy that's sent out that travels at the speed of light. And then slow time, that's the platform that's traveling. And no matter how fast your platform is, whether it's a satellite or a missile or an airplane, it's going to be much slower than the speed of light, which is why it's called slow time. So yeah, that's actually more intuitive terminology, but that's what creates your X and Y height and width of the image. But it doesn't really translate directly because you're not collecting X and Y, the pixels that you would in a normal image. You're actually collecting a fan, right? Because you're sending out pulses as this platform moves, and that movement of the platform is what's creating your aperture. So aperture in regular images, you have a big telescope, a big lens, and that's what's responsible for giving F number, focal length. Well, with SAR, your aperture is created by the movement of the platform. And so, range or fast time resolution in imaging space. Yeah, like I said, it's fast time is speed of light, the pulse that's sent out into the world. Slow time is the movement of the flight. And so what's interesting about this and why distance doesn't really play a factor is your fast time dimension is limited by your bandwidth. So how powerful is your radar? What's your bandwidth? And so a lot of the commercial satellites up until a couple years ago, their maximum bandwidth was 600 megahertz. And so that's going to be what limits your cross-range resolution. Whereas range resolution, as long as you're staring at that same spot, there's no limit to how much range resolution you get. It's just, how do you stare at a spot for that long? That was really the limitation. But now with the amazing satellites they have these days, they can stare at a place for a long time. They can IOPSR on one location. And so back even a couple years ago, a lot of times they were limited by range resolution because they didn't have the gimbals that would allow the satellite to stare at one place. They were limited to the time that they were passing through that area. But now that they have gimbals, they can stare at one area for a really long time. And now the limitation more is the bandwidth. And so that's the trade-off. And so distance, to this extent, doesn't matter. So yeah, so what is a component of resolution that's missing compared to EO and IR? Anybody? I just said it like 3 times. Distance. All right, so how do you get color in SAR images? There's a lot of different ways. One of the older, more common, well, actually it's not that common because polarized SAR is not that common. But one of the more older ways was polarized SAR. So they take each type of polarization, pack it into one image and create RGB channels out of that. So here I'm showing the HH polarized in red, the cross poles in green. So this only says HV, but a lot of times we'll actually add and double the cross poles. So radar that collects polarized or polarized radar will have 2 transmissions. And so it'll have, it'll collect, well, I guess 2 types. So if it has one HH transmission, it'll collect whatever the monopole or HH pole is and the cross poles. And then if you have the other VV, then it'll collect VV, what comes back as VV, and the VH. So what gets cross pole. And so if you're able to collect all 4 because you have 2 transmission transmitters, and then you have 4 channels. And a lot of the times what we do, because the amount of energy that comes back as cross polarized is much, much lower than the direct polarized, we'll actually add the 2 cross poles together and double it. Because it's about a quarter. The energy that comes back for cross pole is usually about a quarter of the direct poles.
So what is H and V, and what does that imply about the returns that come back from the scene?
So H is the horizontal and V is the vertical. So light, even incoherent light, has all the different directions that it travels in. So with radar, because we're controlling what we send out, because we're able to manipulate what gets sent out, we're able to send out either an H, which is the horizontal, or a V, which is the vertical. So light that's facing this direction, or light that's facing this direction. Then depending on what that energy hits, it'll either come back directly, which it usually does, or because it runs into something in the world, it'll change its polarity. So yeah, a lot of times we'll do different tricks to normalize the amount of energy that's in each channel. So that's one way to do it. So polarized SAR have been viewed as something that's colorized for a long time, for a few decades now. And then another way to do it is to use a heat map. So this is kind of cheating because it's not really relating anything to the wavelength. It's just assigning a different color to the different magnitudes, which is the image I have down here of a SAR image of the CFD logo. And so, yeah, I colored it in the yellow-blue heat map. So those are 2 of the common ways that SAR images are colorized, but we're not here to talk about that. We're here to talk about colorized sub-aperture images. And as the name implies, it's colorized because of the sub-apertures. And it's possible, and it's becoming more popular these days with commercial companies because of the long dwell times that are capable. Before, when the long dwell times weren't possible, you're just trying to be able to see something. But now that we're able to stare at an area for such a long time, we're actually able to divide that up. So we're not only just trying to see what's on the ground and have enough spatial resolution, we have plenty of spatial resolution. Now we want to see something more. So colorized sub-aperture images, what is it? So it's assigning a different color to each sub-aperture. So a synthetic aperture is created by how long a plane or a satellite moves across an area and how long it's able to stare at it. So with regular EOIR images, your integration time is what, microseconds, right? Very, very short amount of time. With SAR images, it's very common to have 10 seconds for integration time. So very different. That's a long, 10 seconds is a long time. A lot of things happen in 10 seconds. But yeah, these days, companies like Umbra, Capella Space, ISI, they're able to stare at a place for 20 seconds plus. But it comes at a cost, right? In 20 seconds, what can happen? Anybody? What happens? What can happen in 20 seconds?
Targets move.
Exactly. Targets move. A lot of things can move in 20 seconds. A wind blows, leaves in a tree will rustle. Yeah. If your integration time is microseconds, that doesn't matter. But if your integration time is 20 seconds, that's kind of a big difference. So yeah, but then 20 seconds, if you divide it up, because now you have plenty of pixels, then you can divide it up and you can see, you still have enough resolution, but now you don't have to deal with all the smear and noise that comes from staring at a location for a long time. So what they do is they assign a different color value to each sub-aperture, to each section of how long they were staring at, and then they normalize it to create new pictures. So any questions so far?
That's a good question.
Yes.
So, you have some antenna, there's some dish that's following all that collected radio frequency down to a single wire that goes to something like that, correct?
No, there's no dish. So that huge dish is actually created by the flight. So whether it's a plane or a satellite. So
But you have some aperture that's collecting.
yes.
Only with single channel, not multiple channels that you're sending that any information to. Or is there?
No, it's just collecting the energy that comes back. So you're sending out energy, and then you're listening, receiving that energy, and you're receiving that energy as you fly over some area. And so yeah, you're collecting that energy as it comes back, and it's coming back as complex radio wave signals. So the IQ signals. And then that gets all collected as a history, which is why we call it phase history. And then it's processed. So there's a lot of things that go in before it even becomes an image. And so, yeah, that's actually not a stupid question. It's a very complex question that probably requires a little more discussion. But yeah, all that energy is just collected by the receiver. And yeah, it gets sent to this receiver that records all those signals. And then it gets processed. So initially, all those signals, it doesn't look like anything like images. In fact, it's just all complex garbage. Yeah. All right, so this is one example of a colorized sub-aperture image. Unfortunately, SAR is going to be SAR, and a lot of it still looks black. But you still see cool colors, right? And the reason for those colors is in this particular scene is because you have those curved spaces. So if you have curved objects like that, when you send out an energy, at some point, yeah, if you have a circular, at some point, the energy is going to come right back to the receiver because of the angle at which it impacts, right? So at all other angles, the energy directs away from the sensor, but at certain angles, it comes right back to the sensor, which is why that color, you see those colors all spread out like that, because at those angles, that energy was coming right back to the sensor. And so it was being recorded as a returning power. So yeah, you usually see that rainbow in curved objects, curved buildings, and even cables. They're curved. So it's a very small amount of power, but at some point in a cable, as thin as it is, energy that's directed towards that comes right back to the receiver. Granted, small amount, but yeah. But in a big building like this, that power that comes back is a whole lot more. So that's why you see the color. But most things don't really change with the aperture direction, and so it's still black and white. So black is where there isn't that much energy that comes back because it's grass or sand or something flat. So with visible light, you measure it in nanometers, right? So it's very, very small. With X-band radar, the wavelength is something in the order of centimeters. Well, so X-band is 1.2 centimeters. And so anything that's smaller than 1.2 centimeters is considered smooth. Which, like, that's kind of huge, 1.2 centimeters. But yeah, for the radar, 1.2 centimeters is will be invisible. Yeah.
This is a good image. Maybe you can just kind of briefly talk about what we're looking at. What is it a scene of, and which direction was the plane flying? What imagery?
So this is an airport, and you can see that the plane was flying, I guess, on the other side, just because of the directionality of the colors. So it's going from red to blue, and so it was flying, I guess, the opposite of the red to blue, right? Because the sub-apertures for the red was the beginning, and then as it goes along up till the blue, that was the end of the sub-aperture.
How are you assigning colors again? Is it based on the magnitude or magnitude of the intensity?
Yes. So all of this, all SAR images, or yeah, any SAR images is based on the magnitude of the return. But now that magnitude of the return is normalized by the color scheme based on what is returned in each sub-aperture, in each slice of the collection. So yeah, as it goes from red to blue, that's kind of the direction of the flight, direction of the sub-aperture. So the beginning of it was red, and towards the end it was blue. Yes,
Is that kind of like you're taking smaller azimuth apertures?
Yes.
And that's what was responsible for each color you're assigning to it?
yep.
Okay.
So each smaller azimuth section is being assigned a color.
Are you gonna walk us through what we've learned from the color?
So this scene, you know, what you're learning from the color is, you know, the curved buildings.
Would we not see that without the color?
Yes.
We would see that without the color, or you're saying we would not see it?
You would see that without the color, which is why this is not that interesting. It's just nice to see, right? But this image, I guess, so a lot of the times when we're looking at SAR images, it's kind of hard to interpret just on its own. So we'll take a regular passive image to compare it to. So yeah, many a times I've taken SAR images and gone to Google Earth to put it side by side to see what I can interpret. But a lot of times you can see, once you have a baseline of what you're looking for via Google Maps or something else, now you have a point of comparison. And so this image on the right, some of the things that you would not normally see is, well, kind of mapped out. So you have your structures that would be really hard to see in a regular image. That shows up, lights up like Christmas tree on a SAR image. And so an image like this, the color would brighten some of the objects that would be hidden in a regular EO image.
Is that
EO
Cedar Point?
image. Sorry?
Is that Cedar Point?
Yes. Yeah. So yeah, it's the park, amusement park. So it's kind of hard to see all the, what do you call those things? Roller coasters, right? I mean, you can't really see them in the EO image, but they show up like Christmas on the SAR image, all the structures, all the wires. And that's why it's hard to see on the EO image, especially from space. You can't see the wires that the roller coasters have, but they show up like Christmas on the SAR image. Yeah, and this is kind of the close-up. So that's that same area. You see pool, but there's the roller coaster and all the different wires that show up in color. So actually, even without color, you probably could see that a little bit, but it wouldn't show up as much because it would get normalized. It would get eaten up in the normalization process. Because with SAR images, you're adding everything up. And so if something, an energy comes in only one direction, it just gets averaged out.
And it's also, you mentioned in a previous image that the saliency or whatever pops out is also determined by the path the plane takes
Yes.
from the sensor.
Yes.
Do you do multiple passes in different directions or something? And
Yes.
try and-
All the time. But yeah, that has to be available, right? Sometimes it's not that hard to take multiple passes from all directions, but yeah. Ideally, yes, we would.
So I'm thinking in the two insert images, the
Mhm.
optical one, we're looking straight down,
Yes,
right? And the SAR one, it sort of appears that we're seeing the roller coaster from the side. Is that true? Are we seeing elevation differences?
so with SAR images, you're always imaging from the side, right? But at the same time, you're also projecting it onto the ground. So that roller coaster, because it has some level of height, the energy from that roller coaster returns faster to the receiver. And so the receiver thinks that it's closer to the sensor than it actually is. And so that's a phenomenon we call layover. And so that height difference causes any object with height to kind of lay flat on the ground, like it's collapsed. Yeah. But yeah, with satellite images, you're usually looking at it straight down. I guess with the satellite, well, not with satellite, but if you're taking a passive imagery from the side, you would see the roller coaster. You might not be able to see the wires because that would require really high resolution. But yeah. So now this is where colorized sub-aperture images really shine. So any guesses as to what those streaks are, those colorful rainbow streaks? This is Atlanta Airport. Yes, on the right.
It looks like traffic on the highways moving.
Yes, yes. And they're moving cars. Normally they would be averaged out because they're moving. But with colorized apertures, you're actually able to capture them as they move. But now this is Atlanta Airport. You see that rainbow streak in that direction. Why don't you see any cars in the other direction? I mean, it's still a busy highway. It's Atlanta Airport 24/7. They're always going to have a lot of traffic, but why don't you see anything on the other side? Yes, that's exactly what it is. So to the radar, because the vehicles are moving at a direction perpendicular to the aperture, it's essentially invisible to it. And so that's a problem that's been, I guess, plaguing the Missile Defense Agency for a long time. But yeah, anything that's moving at a distance perpendicular to any kind of detecting radar aperture is invisible. It falls within the ambiguities of the angle of arrival. But in the other direction, you can't resolve it because right now we're resolving it to the ground. But you can still see it. But you wouldn't be able to see it if it wasn't colorized. It would just get averaged out. Yeah. Any questions? Yes.
So I don't know a lot, like I hardly know anything about SAR, so it's probably a basic question. What are the sort of like key collection parameters that like determine your vertical resolution that you get in the scene?
Bandwidth and dwell.
Bandwidth and what?
Dwell.
Well,
So how long we stare at an area. So the longer we can stare at it, then the better resolution we can get. And then bandwidth, that's just your radar, your hardware. Well,
so the angle,
kind of.
it's not angle dependent.
Not really. So the image that you form depends heavily on the angle, but it's also dependent on what you're seeing. So if you're trying to see the side of a building and you're collecting directly against that, then that whole side of the building is going to bounce the energy right back into the sensor, which means it's going to bleed everything else out. So you don't really want to do that. What you want to do is not be directly perpendicular to the side of the building. Pretty much, but yeah, angle is taken into consideration, but a lot of times, especially with satellite imaging systems, you collect what you can get. right? You stare at a place because it's able to pass over that place at a certain time in its orbit. And so you're able to control where it's staring for some amount of time, but after that satellite passes over that area, then, well, tough luck. But ideally, in a perfect world, we'd want to collect from all 360 angles. That's your perfect world. Drive circles or fly circles around a certain area. Any other questions? Okay. Oh, and then the image on the left. So that's your bridge. So you should be able to see that in most cases, although it looks blue, which means the return was highest towards the end of the aperture. But what do you see above the bridge? It's very faint, but you can still see it.
Suspension bridge?
Yes, so those are the suspension cables. And so, yeah, suspension cables normally wouldn't show up in satellite PO imagery because it requires a really high resolution to show up. But with radar, it's faint, but you can still see it. And it's because cables are essentially circular structures. And so at certain angles, the energy that goes out comes right back to the center as it hits that cable. Which is why it shows up more as a rainbow, because the direction at which the energy comes right back to the receiver changes as the aperture flies over. So it's able to detect that very small amount of energy that comes back from hitting such a small object. Yes.
So is it very material dependent that what kind of targets will be the using that?
Yes.
Like in our previous example, as well, you saw the metal cable here also.
Yes, very much so. So what radar energy is returned is material dependent, because some materials will absorb radar. People don't absorb radar energy. So people don't image very well or don't show up in SAR images very well. Yeah, and then metal obviously tends to return energy much more. Yeah, and natural objects, grass, trees, they do return some energy, but they tend to scatter it more, which is why, yeah, grass and trees tend to, unless you're imaging a place with only grass and trees, it's kind of hard to see them, or they'll show up pretty dark. Yeah, and buildings, obviously, they reflect a lot of the energy. They're very reflective. Yeah, so that's a really good question. So material does have an effect, but very differently from regular passive light. So passive light, each material has its own spectral signature. So, and I guess with radar, you can kind of say the same thing, but the math is a little different. Questions? I don't know if I have any more slides. All right, so I think this is my last slide before my conclusion. So what can't we see? Moving objects, because we're assuming everything's on the ground. So I say kind of, because there's a lot of different tricks we can play. And, you know, as you saw, they come up as smears, rainbow smears, moving objects. So that's kind of the extent we can see them, but you know, we can't say, oh, that's a car. Well, we can say it's a car because it's near the freeway, but you can't really resolve them. Yeah, and then if it's moving at a direction perpendicular to aperture, then it's essentially invisible to the sensor. Yeah, and then color. We're creating color artificially, but it's not the same way color is formed in regular RGB images. Right? So we can't really see color with our images. Not really. We're inserting color, but we don't really see color. BRDF. So direction is very important in SAR, but it's not an inherent property in an object the same way materials are for regular passive imagery. So Dr. Bachman's CHIPS class, I'm sure you learned a lot about BRDF. So you don't really get the same thing with SAR, but directionality is very important. And understanding BRDF will give you an insight into how the SAR images work. You don't see BRDF, whereas if you take an image of a metallic surface, you do see BRDF, right? Because there's a bright spot in that image of the metallic object or a round metallic object. Right? So, and then smooth surfaces. A lot of times with smooth surfaces, the energy reflects right away, away from the receiver. So that's what happens to most of the energy, actually. It goes away from the receiver. So what comes back to the receiver is a very, very small amount of energy. It's actually 1,000 of what is sent out. And we're scaling that to be able to see something. Yeah. But what can we see? We can see through darkness, we can see through clouds, we can see through foliage, depending on the band that you're using, and other coverings that's essentially invisible to radar. So tarps, radar will go right through that tarp. Radar energy will go right through the tarp. And so you'll be able to see what's underneath it. Yes. Yeah, so there's certain things, and yeah, you can see, you can't image or resolve what's inside tunnels, but you can essentially send energy into tunnels and cavities and see what comes back out, because it'll bounce around the tunnel, and as soon as it hits something, it'll come back out, come back to the receiver, and you see it as filming. So in some ways, you can see inside cavities and into tunnels. Thin cables or power lines, something that would be difficult to see in regular passive imagery. And then height differences. So like Dr. Erickson said, there's anything with height, you'll actually be able to hit. And while it shows up in a different location than where it actually is, you're still able to see you can still see the structure of what it is. So yeah, that's all I have. Any questions, comments?
Yeah.
Any of my students first? Come on. The bandwidth is fascinates me. So you have about 2.5% bandwidth compared to, I guess you have like a 25 gigahertz signal. Is that about right?
Oh no. So the older radars, the commercial radars had like 300 megahertz bandwidth. But then like the newer, I think Umbra is the commercial radar with the highest bandwidth. They have 1.3 gigahertz bandwidth.
But what's the center frequency that those are operating?
So center frequency will depend on the band. So X-band center frequency will be 10 gigahertz. If you're working with MIMO, then it would be, I guess somewhere in the megahertz. We work in that band, but yeah, P band would be longer wavelengths.
So your fraction of the bandwidth to the carrier frequency basically suggests that it's not very coherent. It's temporally coherent. in a
Yes.
sense, right?
Yep.
And so how does that temporal coherence, I mean, you can imagine using it to your advantage or to your disadvantage. So how does that kind of show up? Because it's going to kind of blur your measuring interference phenomena, I guess, basically interference of these waves. Try to then unravel what's going on there. So if they have multiple frequencies, they're going to be interfering in different ways. So how does it affect your image quality, your resolution, and this kind of stuff? Generally, do you want more coherence if possible, or less bandwidth, more signal but less bandwidth maybe, or do you want broadband?
So you want as much bandwidth as possible, but yeah, like you said, that comes at a price. And it's not really true, full bandwidth. It's actually a chirp function. So it's a compressed bandwidth. This is why, and we compress it because any higher frequencies like that don't have enough energy to come back, which is why we need to compress it as a chirp signal to be able to send it out and to receive it back. So it's, yes, temporally correlated, but it's also compressed as a chirp signal. So that's where.
Anybody who has more questions about how SAR works, we can direct them to Dr. James Albano, who's sitting in the back, who has developed some courses and is here as a staff member in our center. I think maybe one more question. In the visual imagery, the color imagery world, the hot thing now is applying deep learned networks to do recognition and so on.
Mm-hmm.
Can you comment, or do you have any comments about how deep learned networks may be used in interpreting SAR imagery, which fundamentally is harder for a human to interpret to begin with? But do you have any thoughts on that?
Yes, I have a lot of thoughts on that because I work a lot in that space. Mostly they call me in because it doesn't work very well. Yeah, if a lot of you might be doing machine learning, but how it works is, you need a lot of data and you do some kind of regression to learn. But with SAR imagery, every angle changes how it looks, and not just every angle, every radar changes how it looks. So if you're doing a X-band radar, it's going to look from a P-band radar or L-band radar. And even a regular X-band radar, even if you're looking at all X-band radars, how you send out the signal is going to be user dependent. So if you can have full 1.3 gigahertz bandwidth, but you don't have to use all of it. You can actually send out a 300 gigahertz bandwidth just to collect more images. And so all of that changes how a object looks. So if you're simply trying to detect some objects, you need that many examples of that object of all of those different parameters. How easy do you think it is to get all the, it's doesn't happen. So there's been a lot of work to try to apply machine learning to radar images. And some have been successful, but most have not, just because of how particular radar images are. And half the time, the people developing these algorithms don't really have a knowledge of how radar images work. And that's where the problems come in, because you kind of need an understanding of how these images are formed and the physics behind it to really make the machine learning algorithm do what you want it to do. And actually, I think with the first year grad students, I was telling them, yeah, it's great to learn about machine learning and it's a hot topic these days. But what will always be useful is domain knowledge. And guess what you guys have? Domain knowledge.
Well, thank you.